In this talk, I'd like to present our work on graph algorithms in the distributed setting. It should be no surprise that the graphs that we deal with these days are very big. And to give you an idea of the size of the graphs that are available out there, let me give you a few examples. So the largest publicly available graph, the Hyperlink 2012 graph, has over 200 billion edges. In a recent paper, we actually worked with a graph that has over 6 trillion edges. And actually, later in this talk, I'm going to present some results from that paper. And if we ever would like to process the graph behind the human brain, we should be ready to process graphs of hundreds of trillions of edges. So the topic of this talk is how to mine graphs that have billions or even trillions of edges. What are the involved challenges and the techniques for addressing them? At a high level, there are two approaches to processing very large graph. In this talk, I'm going to present the distributed approach in which we have thousands of machines, which means we can also use thousands of CPUs and, of course, many terabytes of RAM. In the next talk, we're going to show how to deal with graphs that are also large, but need to fit in the memory of a single machine. So I'm going to talk about shared memory, multi-core parallel setting, where we have one machine, maybe hundreds of logical CPUs, and up to 1 terabyte of RAM. And actually, we'll see that we can still handle pretty large graph in that setting, but that's coming up next. So the plan for this talk is first to introduce the challenges and some high-level techniques and approaches to dealing with large graphs. Then we're going to look at an example problem of finding connected components. And then finally, I'm also going to present some new ideas, some extended models of computation that are useful for dealing with large graphs. So let's start with the challenges part. So whenever we're running a big computation involving multiple machines, it would be great if we could just reserve all of those machines and they would all only run our computation. The practice isn't that easy, and in fact, we're typically running in a shared data center. The machines are handling multiple tasks, and our job is just one of many. And this, of course, creates some challenges. So let's maybe start with the goals that we'd like to achieve here. So in addition to the obvious goals of achieving high speed and scalability, we also care about reliability. We want our computation to be robust to, for example, hardware failures. And in addition to that, what is maybe less obvious is that we would also like to be mindful of the cost incurred by the computation. So what exactly does that mean? Let's look at the plot on the right side of the slide. So this is the capacity in an example cell used by jobs of different priorities. So as you can see, the jobs of very high priority, those that we really don't want to fail, occupy pretty much all of the available capacity in a cell. And in addition to that, another maybe 50% of the capacity is occupied or used by lower priority jobs. So what is actually the capacity used by those low priority jobs? Well, as it turns out, there is a lot of resources that are reserved by high priority jobs and not used. And we can actually take advantage of them and run other jobs there, but we would not have any strong guarantees on them running successfully, because whenever the high priority jobs experience a spike in the research usage, the low priority jobs will be preempted. So this is a typical setting in which we operate in, and this actually means that whenever we run a computation, our job needs to be very robust to failures, preemptions, and we need to save all data to persistent storage as disk. But in return, we get a very, very low resource cost because we're basically using the unused resources. Another challenge lies in the data itself. So this plot shows the cluster sizes in a web graph of over 8 billion nodes. And as you can see, while most of the clusters are of very small size, there is one cluster that has almost all nodes of the graph, over 5 or even almost 6 billion nodes are contained in one cluster. So our algorithm needs to be designed not to put all nodes of that cluster on a single machine, because that would of course slow down the computation significantly. To help us deal with these challenges, a number of distributed computation frameworks have been designed. So they provide a high-level abstraction over the distributed setting. They handle communication for us. They provide fault tolerance in a transparent manner. And the frameworks that we typically use run computation mostly in synchronous rounds. And while in the remaining part of the talk, I'm either going to focus on the theory or on a specific computation framework. We often work with jobs implemented using Flume. Many of these frameworks provide a very similar model of computation. So whatever I'll be presenting actually carries over to other frameworks. Let's now look at distributed computation, what it looks like in more details. So this computation proceeds in synchronous rounds. In the picture on the right side, each row represents one round. Each column is one machine. We have one copy of the machine represented in each round. And between two consecutive rounds, there is a synchronization barrier. At the end of the round, all machines wait for the slowest one, and then once all machines finish a computation in a round, the next round starts. So within a single round, each machine receives messages from previous rounds or reads a part of the input, then it performs some arbitrary computation, and then it sends messages to other machines. And then all data which is communicated is saved to persistent storage in order to achieve fault tolerance. What are some desirable features of a computation like this? Of course, we'd like to achieve low running time, and this translates to having a low number of rounds, ideally a constant or maybe logarithmic in the input size. We also want each machine to process its input efficiently, so we want it to run an algorithm which takes maybe near linear time in the input size. We want machines to do a balanced amount of work because of the synchronization, we always need to wait for the slowest machine. And also we want to limit the amount of communication. Ideally, the communication is linear in the input size in each round and balanced among machines. So those desirable features have been captured in a theoretical model of distributed computation that was first introduced in a paper from 2010. This is called the MPC model, which stands for Massively Parallel Computation. In this model, we have an input of size n and m machines of space S, where the total size of all the machines is barely big enough to store the input. Now, an important restriction is that the space per machine is strictly sublinear in the input size, which means S is n the input size to some power epsilon, where epsilon is a constant between 0 and 1. This is a theoretical model that actually I'm going to be talking about in the big part of this talk, but it actually captures most of the distributed computation frameworks that I showed a few slides back. So far, what I designed is what I presented is a model in which we have some number of machines that have bounded memory. This is not yet the end of the definition. There is also a very important restriction of the MPC model, one that corresponds to the load balancing requirement. And it says that each machine sends and receives data of size O of S in each round, where S is, again, the space available per machine. So now with all of this, with this additional restriction, we also assure that the computation is balanced across machines, or at least the communication is balanced. So as long as the machines run an algorithm which is efficient in the input size, the computation is going to be balanced. And here the goal is to minimize the number of rounds subject to all of these constraints. So now let's look at an example problem of finding connected components. Here the goal is to partition nodes of an input graph into sets such that two vertices are in the same set if and only if there is a path connecting them. So you have an example in the bottom part of the slide. This is a very fundamental problem with many applications. You can use connected components computation to do clustering. It's also easy to compute hierarchical clustering using connected components. Of course, you can also use it to deduplicate your data. But in addition to that, it's a very fundamental problem, a building block for many algorithms. And in a recent survey among researchers and practitioners, connected components was identified as the most popular graph computation. There has been a fair amount of work on solving connected components. There are many efficient implementations. There are also many theory algorithms in the MPC model. Here, I'm just giving you a very high-level overview. I'm going to talk about both an efficient implementation and state-of-the-art theory result in the following slides. So let's first look at an algorithm for computing connected components. This is an algorithm that can be implemented in the MPC model, and also it's a high-level description of an algorithm that we actually implemented. So the algorithm is as follows. While the graph has any edges, we repeat the following steps. For each vertex v, the vertex picks its label, which is a random number chosen uniformly from the interval between 0 and 1. And then for each vertex v, we look at all the neighbors and we find the neighbor w, which has the smallest label. And this neighbor w is then assigned to or defines the value best of v. Now we group vertices by the value best v, and we merge them together within each group. So what you can show pretty easily is that in each iteration, the number of vertices shrinks by a constant factor. And then this actually means that the algorithm requires a log n number of iterations. It can also be shown that each iteration can be implemented in a constant number of MPC rounds. This is maybe not obvious from the pseudocode, but what I think is pretty clear is that this is a highly parallel algorithm. And then in addition to taking log n MPC rounds, it's also interesting that this algorithm with a slight tweak actually takes only log n rounds if the input graph is random. So this algorithm is actually very efficient in practice. Here is a comparison of the running times of this algorithm shown in the first row to other algorithms in a similar setting. And as you can see, it's in most cases, it is the fastest one. It is one of the two that we were able to run on a 6.5 trillion edge graph. And in that case, it's roughly 3 times faster than the other baseline that managed to solve that instance. If you're curious about specific running times, they're from maybe 2 minutes on the smallest graph to some low number of hours on the largest one. On the theoretical side, in the MPC model, connected components can be found in roughly log n plus log d rounds, where d is the diameter of the input graph. And this actually is has the nice property that because in real-world graph, the diameter is typically polylogarithmic in the input size, this algorithm in these cases takes log n rounds in total. Now it's a theoretical algorithm. It's probably not as efficient as the previous one in practice, but connected components is also a problem that's heavily studied from the theoretical side. On the lower bound side, it is widely believed that connected components requires log n MPC rounds, and this actually is a conjecture that's used to infer hardness of many problems in the distributed setting or in the MPC model. But for the rest of this talk, more important than the conjecture itself is the problem behind it, the problem that is conjectured to be hard. As it turns out, the following seemingly easy problem is actually the reason why connected components probably cannot be solved faster in the MPC model. So here, the input is promised to be either a single cycle on 2 n nodes or 2 cycles, each containing n nodes. And it's believed that distinguishing between just these 2 inputs requires log n rounds in the MPC model. So let us try to understand what is the hardness in this problem. Intuitively, in order to solve it, we should aggregate some number of consecutive nodes on one machine. But in the MPC model, this is actually not something that's not very easy. If we assume that each node knows the identity of its neighbors, and we even are able to aggregate k consecutive nodes along the cycle on one machine, then well, basically, the only thing that seems to be possible in the MPC model is to communicate with the neighbors of the nodes that we know about. So from the state in which each machine knows about k nodes, in maybe 2 rounds, we can go to the state where each machine has 3k or knows about 3k nodes along a cycle. And it's highly unclear how to do better. And because of that, the problem is only known to be solvable in logarithmic number of rounds. Now, what is the fundamental problem here? Well, the problem is that when we know a node, all you know in addition is just its neighbors. A possible workaround is to give machines random read access to the graph. So let's say the machine, knowing the identity of a single node, can now start traversing the cycle. This actually allows us to bypass this hardness and solve the problem more efficiently. Let's look at this idea more closely, because we will later show how it actually leads to a slightly different approach to distributed computation than what's captured by the MPC model. So let's assume the input graph is stored in a distributed hash table, and then machines can read this hash table adaptively within a single round. So if, for example, we assume that the input graph is a collection of rooted trees, each node knows its parent, and then a node can find the root of its tree in a single round, just by following the parent pointers and querying the distributed hash table adaptively. And this kind of property or algorithm is used in the implementation of affinity clustering algorithm that was mentioned in section 1 of the workshop. If this idea still sounds a little bit vague to you, let me now formalize it. So we introduced an adaptive MPC model which formalizes the idea of running an MPC computation extended with a distributed hash table. So this model is a modification of the MPC model, and the difference is that all messages sent by all machines within a round are saved to a distributed hash table. This is shown in the picture on the right side. And then in the following round, each machine can adaptively read O of S values from the distributed hash table, where S is the available space per machine. So here we have the same bounds on communication as in the MPC model, but the difference is that the machine, instead of being given some input data, can choose what to read adaptively within a round. So I'd like to stress that within a round, each machine has an input distributed hash table, which it can read adaptively subject to the constraint on the maximum amount of data communicated, and it can only write to another distributed hash table. So the input table is read-only, the output table is write-only within a round. And then the write-only table becomes a read-only table in the following round. So there are some natural questions about this model. First of all, we're allowing machines to issue a potentially long sequence of reads. So there is a potential concern that this may actually be slow when implemented in practice. Actually, as it turns out, reading data from a remote machine is an operation that is currently supported by hardware. There is a technology called RDMA, Remote Direct Memory Access, which allows one to read data from a remote machine in just a few microseconds, which means it's just maybe 20x slower than reading data from local memory. Another concern is about fault tolerance. Here, again, the properties seem to be pretty good, because within a round, the machines work independently, assuming that they have access to the distributed hash table. But since the distributed hash table is immutable within a round, the input one, whenever a machine fails, it just suffices to restart it. And of course, we need to rely on having a fault-tolerant distributed hash table. So we use this theory model to derive better theory results compared to the MPC model for a number of fundamental graph problems, like maximal independent set, connectivity, minimum spanning tree, and approximate matching, we're able to improve the round complexities from super constant to just constant in the adaptive MPC model. What is also interesting is that the state-of-the-art MPC algorithms are in some cases pretty complicated, while many of the AMPC algorithms that we develop are actually pretty easy and implementable. We implemented our AMPC algorithms and evaluated them empirically, comparing them to the MPC implementations. So specifically, the things that we were comparing were as follows. For the MPC algorithms, we implemented them in one of the distributed computation frameworks that I showed in one of the earlier slides. And for the AMPC algorithms, we additionally extended the model or the framework by running a distributed hash table. And we allowed the algorithms to read from one hash table within a round and write to another one. So because of the different model, we also were able to use a different algorithm in the AMPC setting. And as we can see in the AMPC setting, we get very good speedups. We get a good reduction in the number of rounds, and the running times are better, up to maybe 7x. We studied 3 fundamental graph problems: minimum spanning forest, maximal independent set, and maximal matching. We also ran some experiments with connected components, but what we learned is that the existing MPC implementation is very fast, and improving upon it was not possible with our AMPC implementation. Let me now present a different idea for distributed computation. The AMPC model allows us to solve many problems faster, but there are actually problems which are still hard to be solved. For example, in the shortest path problem, it's hard to solve both in AMPC and MPC model. Well, by hard, I mean that the best known algorithms for exact shortest path require a number of rounds which is linear in the number of edges on the path that we want to find. In order to deal with a problem like this, we developed a new framework for dealing with large graphs, which we call asymp. And the name comes from the fact that it's based on asynchronous message passing. So no more synchronous rounds, all the messages communicate asynchronously. This actually poses new challenges. We need to deal with fault tolerance differently. The checkpoints are done periodically, which means that when a machine fails, not only we have to restart its state from the checkpoint, we also need to replay all the messages that were sent to it between the last checkpoint was made and when the machine failed. In return, we get very efficient CPU utilization. There is no idle time waiting for the end of the synchronous round. We get very good performance for problems like shortest path. But one open question is what other problems this framework can be used for. So let me summarize. I've talked about solving problems on very large graphs using distributed computing. And as I've shown, this introduces many interesting questions on the boundary of algorithms and systems. We've seen how distributed systems allow handling graphs of up to trillions of edges. And then we also presented some extensions to the standard model of computation. For example, we've seen how giving machines read-only access to the input allows for significant speedups. So these solutions work very good for extremely large graphs of trillions of edges. But actually, what about graphs that are a bit smaller? As it turns out, these for graphs that fit in memory of a single machine, these solutions are not as fast as they could be if we used a dedicated solution, because the overhead and the usage of resources in a distributed system is typically pretty significant. So in next talk, I'm going to show how to work with graphs of up to 10 billions of edges on a single machine and achieve very good running times. Thank you.